Cool. Yeah. So thanks for having me talk today. I'm going to be talking about something that's kind of slightly simpler than some of the modeling that has been spoken about in the session so far. So I'm going to go over just my implementation of general linear models when looking at MEG data, but it can also be applied to EEG data. And it's mainly going to focus on specifically how to get it working in Python. So there's a collaborator I work with in Oxford who's made a toolbox for this. So I'm just going to give an overview of the method and just how flexible it can be. So yeah, so an outline of my talk is I'll just go over the general concept of general linear models. Then I'll talk about building a design matrix and adding in contrast and how that's done in the Python toolbox. Yep, and then I'll talk about permutation testing and then just go over a couple of examples if I have enough time in the 15 minutes I have. Cool, so firstly, general linear models are pretty simple. You can use them for any question where you have observations with some data that can be anything from a single value to multiple dimensions with thousands of data points. And then most of the people here will be interested in looking at this in some brain-derived data. So some scans from an MEG scanner or EEG electrodes. And then you want to look at how that data is predicted by one or more explanatory variables. Again, this can be almost anything. In equation form, it's very similar to almost exactly the same as a linear regression. So you have your data, which is y, some variable that we can represent with x, and then a scaling parameter that represents the weight that that variable has on that data, plus some residual data or error, which is just everything that isn't explained by this variable. To scale this up and show it at a more practical point. So for instance, you might have all of your participants' MEG data. Then you have an intercept representing the group average. And then you might have something like each individual's IQ and their age and an error term. So again, stuff that's not explained by the other stuff. Yeah, and so a couple of possible applications. So on the data side, you could be predicting evoked MEG or EEG data. This could be like an example that I use later, which is an average response to sounds, or differences in evoked signals, so just between conditions. So you might put in a difference field. You can also look at it with resting state data, which is something I also did. You can put in between parcel correlations, averaged epochs, broken down by frequency. Or you can even put in stuff like graphs and connectomes. So DTI-based connectomes, directed graphs, weighted graphs, or whatever connectomics you want to use. And you can put in the whole brain, so all of the data you have, which is what I tend to do, which is where I think the strength is, because you can identify things without having to make a priori selections of data, or you can put in specific sensors or sub-selections of source localized images. Yeah, and then coming to what you can use to predict that data. So this could be group, so a patient group against controls, a treatment group for some kind of pharmaceutical intervention, or a demographic group like socioeconomic status or gender. You can then also put in covariates, so things like age, things that you measure. So these are continuous covariates. So like behavioral measures outside of the scanner, which is something that I've been doing a lot in my PhD, or things like IQ from standardized assessments. And then you can also have trial-based continuous measures. And these are things where you may require multiple levels of GLMs that are kind of layered on each other. And I'll talk about how you can create a model and put that into another model to get some insights. So this could be things like the measure of force on a hand grip over an individual trial for each participant, or pupil size over the trial, or maybe you have some electrodes connected to different parts of the hands to get kind of muscle activation. And you can build a GLM on the individual level and then put the statistics you get from that into another GLM. Okay, so in order to kind of create that equation, you have to first get your data into your model. And so you may have, I'm using an example of my MEG data. So you have in the sensor level, so you have for each participant a 3D matrix of time points, and then sensors in 2D in a 2D layout with an observation, which is now this matrix per participant. And then you create a design matrix, which holds your regressors. So you have the intercept, which represents the mean. And then you can have any number of like parametric regressors, so something like IQ or age. And then you can represent groups in this way as well. So I'll get into why this is helpful in a second. You also notice that these don't really make sense for IQ scores or age, and that's because they are Z-scored and zero meaned, which allows them to be on the same scale, which is important with these types of models. And then you've got your noise and your residuals. Okay, so that's building the model, but in order to test some kind of like hypothesis, you have to design contrasts. These can be expressed in different types of software in different ways. But here I'm going to express them as a set of weights that map onto this design matrix. So for instance, if you want to look at the main effective IQ, you would have a weight matrix like this to represent that contrast. So this is essentially saying that you are not looking at the intercept. You want to look at the IQ scores, but none of the other ones. And those zeros essentially kind of mean that you're only looking at this, and these are accounted for. You could also look at a group difference, and then your contrast would look like this. So you have zeros for those regressors, and then a minus one for group 2, and a +1 for group 1. And this is why having these separate group regressors are helpful, because you can look at direction. So by having this as positive and this as minus, you're basically looking at the hypothesis that group 1 will have a greater effect than group 2. And so you can flip this round if you're looking at the opposite hypothesis. And as I said earlier, the zeros in this case lead to us adjusting for the other predictors. So you're looking at the effect of that thing after accounting for everything else. Okay, so on to how you implement this in the Python toolbox. So this is a Python package called Glam Tools. It's in development, so the documentation hasn't been made for it yet, but you can still get it off of PyPy and work with it like that. So this is maintained by Andrew Quinn at Ober and the University of Oxford. And I found this very helpful because it kind of it deals with a lot of the grunt work when it comes to like building your design matrix and getting your data kind of in the right format. So yeah, you would just have one command for loading in the data, which would just be a matrix, a NumPy matrix, with the first dimension being your observations. And you can also label the dimension labels, which become helpful when looking at the data. So you've got your data, then it has a tool for defining each regressor. So here you have a parametric regressor, and you can just label it age or whatever it is. Also deals with your pre-processing, so this Z scores and zero means everything. And then you put in the number of observations, which will just be the length of this list. So essentially, this is just a list. Also, it has things for defining contrast. So again, there's this object-oriented notation, and then there's this contrast list that I was talking about just in the last slide. And this is the length of the number of regressors that you have. And then it generates your design matrix for you. So you just have a list of your regressors and a list of your contrast. You pass it into this function, and it creates your design matrix object for you. And then you fit your model like this by just putting it into one of its model fitting functions. This is an ordinary least squares model. So I should mention that there's many ways to achieve your GLM model, different methods. OLS is one of them, but the GLM Tools package allows you to use any kind of model that's in Python scikit-learn library. So you can use things like lasso or other penalized regressions like PLS, or equivalents of regressions that return a complete solution, which is helpful if you're doing some kind of statistical inference later. Yeah, so essentially all the way from like getting your data in to like building your model, you just need like basically like 5 lines of code, which is quite nice. So what do the results look like? So for each contrast, you'll get a matrix of weights. So these are these beta weights that I spoke about before, indicating the relationship of that predictor to the input data. So for instance, if we were using an evoke signal over MEG or EEG, the weights for those individual contrasts would show how that predictor relates, or that interaction term or group difference relates to each time point at each sensor. The weights you get in this are on the scale of your data. So for instance, if you were just looking at a simple evoked field, it would represent what change in Ferro-Tesla is explained by IQ, for instance. And from those beta weights, you can derive F statistics and T statistic, kind of like image maps. Sorry, statistical maps. And you generate these by using the betas and the residual error. So you're looking at your signal in context of how much is explained in the overall model. These come out in large dimensional matrices when you're looking at neuroimaging. And so to get kind of like some more interpretation, we can cluster these statistical maps. So here's an example. This is 3D and we've averaged over time. So you get a nice 2D image. And you can see here that there's a cluster of like negative beta weightings, like around this point in the helmet. And so that's more helpful to see this cluster than the individual data points. Cool. But there's a problem with statistical inference here. So even though you can calculate your T-stats or your F-stats or whatever, as many of you know, that this creates problems with multiple comparisons. So you have thousands of test statistics potentially that have been uncorrected for. A really robust option is to permute to create a null distribution. And again, many people will be familiar with this, but in this case, for each contrast, we go through and we shuffle the rows or flip the sign of the design matrix that are weighted in that contrast, and then we keep the other rows fixed. And then we recalculate all metrics. And importantly, this has to include your things like clusters. So you go through your whole kind of like pipeline. You repeat this many times, depending on how many participants you have and how many contrasts you have. This may have to be more or less. And you get a null distribution for each time point in your statistical map. And if your observed statistic is above a given percentile that relates to your alpha level, so for p equals 0.05, you would look at the 95 centile for each null distribution for each point. And if it survives that, it's likely to be true. The main assumption with this is exchangeability, which I find difficult to explain intuitively, but essentially like the joint probability of your distributions has to be equal. In practice, this translates to issues when you have repeat measurements. So if you have like scans at different time points that you're trying to model, or non-independent regressors. There's ways to adjust for this, and I won't go into that using block permutation. But GLM Tools, importantly, implements lots of this stuff. So for doing cluster forming and cluster-based permutation testing, we can do this in one function. So we enter in some settings. So we enter in a cluster forming threshold. We can also use threshold-free cluster formation as well, using M&E. And then you enter the pooled dimensions. So like if you don't want to look at like a 3D matrix, you want to just look at a 2D one, you can collapse some dimensions of your data, which is quite helpful for interpreting stuff. You feed this into the design matrix, data and contrast we defined earlier here. specify the number of permutations, put in those arguments, and then specify the matrix the metrics that you want to permute on, and then that runs itself. It uses some parallelization, which is quite helpful. That's a bit faster. And then using this function, get significant clusters, this just returns these two matrices. One masks all of the significant clusters for you. Another one gives you the statistics. So again, you can do your whole analysis in kind of like a few lines. Cool. So I'm going to go over some examples. I think I've maybe got like a couple of minutes. So I used this recently in a paper to look at mismatch negativity. So I had an auditory evoked potentials for words and non-words, subtracted them and averaged them over participants. That was the data I tried to predict. Used 82 children, put in all of these different regressors, including cognitive ones, attainment from school, age, and income. And what I got out of it is these nice helpful clusters that I didn't have to like pre-specify time periods or spaces that I was interested in the helmet. And I found an education cluster, one related to age, and interestingly, one related to subjective economic status. I've also done this using Connectomics. So I extracted connectomes from resting state scans, and I was interested in how those connectomes, what connections were related to age in that sample. So I used layering of models. So I first calculated a subject level multivariate autoregressive model that looked at parcellations. So this is just a kind of cartoon. Because this was broken down by frequency, you could look at how given parcellations affect activations in other parcellations at different frequency bands. And I also had to do an interesting surrogate data phase shuffling approach to get the intercept right, which I don't have time to go through, but I found quite interesting. And then you get this really, well, what I think is a really interesting output, where I get these big connectomes for each frequency band. And you can kind of look at like 10 hertz, like which parcels are driving activity in each other parcels and which parcels are receiving activity in other parcels. And you kind of get these nice, I can't show you, well, something was supposed to pop up. There we go. So I can create these kind of nice little models where you can change the frequency and look at how connections vary related to age over frequency, which is quite interesting. And I'm analyzing that now to look at hubs in that connectome. So anyway, in summary, because I'm running over a little bit, GLMs and permutation testings are simple but potentially powerful and flexible methods. You can use GLM tools to do this in Python, which deals with a lot of the implementation for you. And if you want any more info about this, then you can email me at this email address. Oh, that's it. Thanks for listening.